Hello and welcome to JHEP's lesson on rates. This lesson is going to be a long one because it's a very long topic. It covers, I think, it covers 7 chapters in the OCR book. But it does cover everything in rates. Okay, so first of all, what is rate of reaction? When you did your AS, you remember that we had that we learnt how molecules collide into each other to overcome activation energy and react with each other basically. In A2 chemistry, we actually know or learn the mathematical term for how fast a reaction goes. We would perform experiments to see how quickly a reaction is in a period of time, and that is what the rate of reaction is. It's the change in the concentration of the reagent or the product divided by the time for the change to take place. Okay, put simply in an English way, rate is the change in concentration of a reactant or product per unit time. So say for example, in 10 seconds it's the concentration halves, and then in another 10 seconds it halves again. That's the rate of that would be the change in that concentration divided by 10 seconds, and the units of it would always be mole per decimeter cube, well, to the -3 per second. So mole per decimeter cubed per second. You do need to know this. You do need to learn this because this is very important to what we're going to learn about today. So, how would you write concentration in A2 chemistry? Because we've got the very long way in writing stuff like concentration, but in A2 chemistry there's a much easier way. We write it in square brackets. Okay, so this means the concentration of NaOH. Okay, that is like the simplest way to write concentration, and again you do need to learn this, you do need to know this for all of rates. So what is concentration? The concentration is the amount of particles in a given space, whether it be in a liquid or a gas or a gaseous state, it doesn't matter. We cannot have concentration in a solid though, so remember that, because examiners will test you on that implicitly. They would probably give you a heterogeneous equation to do, and they might have a solid on there, and then it might and then they would expect you to know that the concentration for a solid does not change, only in aqueous. So what happens if we add water? If we add water, we double the volume of the space of the concentration, but we half the concentration. So say for example, in 10 milliliters of sodium hydroxide, okay, which is in aqueous, if we double the volume of that, so say 20 milliliters, the concentration of this would half. Okay, because the amount of particles in that space has now essentially halved. So what about if we decrease the space for the reaction? This is when we're talking about equations in a gaseous state. This is usually in an aqueous state. The concentration of that reagent would increase because the space has been decreased, so technically the amount of particles inside that given space has increased. So stoichiometry, if you don't know, is just basically the balanced equation that we've always used in AS chemistry. Okay, so this is a stoichiometric equation, and these are no use when it comes to telling us the rate of a reaction. This is no use whatsoever. There is no point of having this. The only reason why we have it, well, you'll see later. But for us to determine how quickly a reaction is happening, we need to perform experiments for us to gain the data to write a rate equation. And the way we do that, let me see if there's anything below that. No. the way we do that is to use a colorimeter. And we can use that especially for bromination when we want to test out if a substance has a double bond or anything. And with bromination, the color would obviously decolorize. It will decolorize, and we can use a colorimeter to test that. So usually we would plot the data on a table like this, and we would check what the concentration is after a set period of time. So let's say 10 seconds, 20, 30, 40. And this would always go on the x-axis, okay? Because this is what we're essentially changing. This is the independent variable. And the concentration of A will be plotted alongside the y-axis, because this is the dependent variable. This is what we're measuring. And we can plot it like this. This is how it would look like if we put it on a graph. We can see that the concentration of this is halving after every 10 seconds. We do need to know what that essentially is, but we'll come back to that later. When we have questions that regard tables like this, we need to make sure that the answers we give are to the same number of decimal points as each of these are. Okay, so let's say, for example, if it says what would be the concentration of A when the time is 15 seconds, we know that it would be 0.075. This would have to be in 3 decimal places because these are all in 3 decimal places. Okay, this is why this is 0.200, 0.100, 3 decimal places. It can be 2 decimal places, but only if all the other separate bits of data are in 2 decimal places. So, as we can see here, there are all different types of graphs of concentration versus time. As we can see here, the concentration declines steadily as the time moves on. In this graph here, we can see, I know it's not very accurate, but we can see that the concentration of it halves after each set of time. Okay, this is what it's supposed to look like this, by the way. And this one over here, we can see that there's a rapid decrease in concentration. Sorry, it shouldn't even look like that. It should be coming out a bit. There's a rapid decrease in concentration versus time. Then it evens out. Okay, we would know what order graphs these are in a minute once you get to know what order actually is. But to find out the rate of a reaction, what we do, especially when it's these type of graphs, we will draw a tangent to the point that we want. Okay, if you do maths, this will be incredibly easy for you because this is just part of differentiation. But we will draw a tangent to the point that we want, and then we would select 2 points over here and then join them up together using a line. Okay, so we could use this to notify the change in X, even though this is supposed to be Y, and the change in Y. Okay, and we can use that to find out what the rate of that reaction is. Okay, so say for example that this is 1/2, I know it isn't, and this is 1/4, and this is, I don't know, 10 seconds, and this is 5 seconds. We know that the rate, the change in X, we know that the change in X is 5 seconds. We know that the change in Y is 1/4 or 0.25. So the rate of this would be 0.25 divided by 5, and the answer would be whatever it is. I didn't calculate it, but the units would be mole per decimeter minus 3 s to the minus 1. So this is the written way of writing it, if that's even proper English. And what we can find out, what experimental things that scientists do, is to check out how much the initial rate changes. Let me rephrase that again. Experiments that scientists do is to check out how much a concentration affects the rate of a reaction. And that is called the order. That is the mathematical term for it, and the chemical term for it as well. The order tells us how the change in concentration of a substance has affected the rate of reaction. These are all basically what you need to learn, but we're going to put this into practice. Okay, if you prefer to just learn things off by heart, definitely learn this. But if you want to know how this actually works, just wait and move on to the next page. So let's say that I performed an experiment with using this, and I want to check out the effect of doubling the concentration of NO2. We can see using these experiments that if we double the concentration of NO2 whilst keeping the concentration of O3 the same, we can see that the initial rate of this reaction has also doubled. Okay, that means that 2 to the power of x equals 2, because the reagents have doubled and so has the initial rate. We should know that the order of this is going to be 1, because when this doubles as well. As we can see here, if the concentration of A has doubled and the initial rate has also doubled, the order is 1 with respect to A. So the order of this, of NO2, would be 1. There. Now looking at O3, we can see that when we double the concentration of O3 whilst keeping, let me just get rid of all this, whilst keeping the concentration of the other the same. Okay, so we're going to keep these two the same. We can see that the initial rate has also doubled as well. Okay, the thing that people might not have noticed is that this is a different power to this. This is 10 to the minus 3, this is 10 to the minus 4. So if you were to write this in terms of 10 to the minus 3, it would actually look like 0.05 times 10 to the minus 3. Then we can see properly that this is half of that. So the order of O3 is going to be 1 as well. Okay, because as we double this, the initial rate also doubles. Now, what is the way to write this in a rate equation? So a way to collate this. I'm afraid I did some data wrong in this, so I'm going to have to, oh no, it's not even here, it's the next one. I'm going to have to modify that. But it would look like this. Rate equals K times the concentration of A to what its order is, so we know it's 1, times the concentration of B to the power of its order, which we know it's 1. Okay, so if we were to write this properly, it would be rate equals K times the concentration of NO2. Is it NO2? Yes, it is. It's NO2 O3. Okay, we can write the 1 here if we want, but if you do maths, you know that anything to the power of 1 is itself. So what is K? K is the constant, it's the number that links the rate of reaction with the reagents. You would get to know what K is and how to calculate K later. And the overall rate is all the orders added up. So 1 plus 1 equals 2. So the overall order would be 2. Now, how would we write this in an exam? Well, as the concentration of NO2 doubled whilst keeping the concentration of O3 constant, the initial rate doubled. Therefore, the order 2 to the power of x equals 2 is 1 with respect to NO2. That's 2 marks. As the concentration of O3 doubled, the initial rate also doubled. Sorry, that's my fault. Also doubled. Therefore, the order, if we solve this, is 1 with respect to O3. Therefore, the overall order is 1 plus 1, which makes 2. So therefore, the rate equation would look like this. There we go. It would look like this. K, NO3, G. I would usually write the gaseous state. It doesn't really matter, but I would write it to O3, 1. And the QWC mark is usually for the 2 sentences where the meaning is clear. And I think we've made the meaning quite clear here. Now, the second bit of the question that they would usually ask you is to calculate K. Right? And, so I've got to remodify this as well. The rate equation is what we would use to find out what K is. So what we would use is experimental data from one of these experiments. Okay, let's use experiment 1. Yeah, let's use experiment 1. So we would basically substitute all these concentrations in. So that would be the initial rate, which is 0.540 over 2.8 times 10 to the power of minus 2 times O3, 1 times 10 to the minus 3. If we put this on our calculator, doing this on the calculator would make 19285.714. To check that is correct, we can use another experiment and substitute the values in. It should give you the same answer. To calculate the units, we need to write mole per decimeter minus 3, S minus 1, because that's the rate, mole per decimeter cubed times mole per decimeter cubed. We can see that we can cancel this out, we can cancel that out, which leaves us with S minus 1 mole per decimeter minus 3. Now, to bring this on top, all we've got to do is invert the powers. Okay, so mole is essentially mole to the power of 1, dm to the power minus 3. We would flip the powers over, so that would make mole to the minus 1, dm to the 3, and then we just put the s next to it, s minus 1. Conventions say that we should write the we should put the positive powers first. That's it, dm3, then mole minus 1, then s minus 1. I think it's important to do that. You should do that. So the answer would be 19285.714. I can't remember what the units are. dm3 mole minus 1, s minus 1. Right. With these orders, we can actually draw graphs to represent it. So with a zero order graph, we know that as the concentration increases, the rate does not change at all. So the graph would look like that, one big straight line. With a first order graph, so that's a zero order graph. With a first order graph, we know that as the concentration increases, as the concentration doubles, the rate also doubles. So it's going to look like that, okay? One straight line passing through the origin. Obviously everything should pass through zero. Concentration equals zero. With a second order graph, we should know that as the concentration increases, the rate, as the concentration doubles, the rate quadruples. So it's going to be a much steeper graph, like so. And so that is what our order graphs would look like. And you need to remember how they look like for the exam. Coming back to these graphs over here, this is called a half-life because after every amount set of time, we can see that the concentration halves. Okay, maybe we should use this one over here. As I was talking about over here, after every 10 seconds, the concentration halves. And this is called a half-life. And this is a first order graph as well. With this graph over here, we can see that the concentration rapidly decreases, but then it slows down. So the half-life over here increases with time. Over here, the half-life is constant. And over here, the half-life decreases with time. And that is it for this lesson. If you want to learn about rate determining step, there is a separate video called Rate Determining Step. I think you should go and watch it.